Hello Kumani, welcome to today's maths video lesson. I hope you're doing well. So today we're starting a new section, the effect of parameters a and q on trig graphs. So you can see how rapidly we're building concepts in grade 10. Just now in the previous section we were looking at how parameters affected a whole set of new graphs, the hyperbola, parabola and exponential graph, and now we're moving directly onto a new application for trig graphs. So the methodology we're going to be following is much the same as we did in the last section. We're going to start off with the simplest cases, our base cases, and then we're going to adjust the parameters. We're going to adjust things and see how this affects the overall shape of the graph and any vertical shifts up or down. So the base cases are given on page 137 of the textbook, and those are the sine, cos, and tan graphs. Now, I know we've drawn these graphs quite extensively in the previous section, but I'm just going to do a little recap here, just to tie everything together. And once again, I'm going to pick points that help me with the plotting, just to get the overall shape. So we're going to start off with the sine graph, and our rhyme for sine is so. Remember the rhyme so katoa. So sine is opposite over adjacent. Okay, and I'm going to pick some values for theta. And the intervals are going to be in 90 degrees. So 90 degrees are like the easiest points to work with for sine and cos. And those gives our peaks and trough of the sine and cos waves. So by drawing a line through the peaks and troughs, you can get an idea of the shape of the wave. So I'm going to go minus 180, minus 90, 0. And for the positive values, 90, 180, 270, and 360. Okay, so I'm going to work out a few of these values using our quadrant method. You can obviously use your calculator to check them. And the reason I'm doing this is just to give a little bit of a refresher on the quadrant method as well. So for the first point, negative 180, we know that positive values go anti-clockwise in the quadrant. So the negative values move clockwise. So we start here at 0 and we go like this to 180. So our hypotenuse is like the arm of the clock, moving clockwise and anti-clockwise. So moving anti-clockwise, 180, our arm lies over here. Okay, so just to remind you, this portion is the opposite and this is the adjacent. And when the hypotenuse is flat like this, it means that it's like a triangle, which is just a line. And in this case, the length of our adjacent is equal to the hypotenuse. So in this case, our adjacent is negative. It's on the left-hand side of the vertical. So the value of our adjacent is negative of the hypotenuse. So this is not important because adjacent doesn't feature in the so rhyme. We only need the opposite and the hypotenuse. And when the graph is flat like this, our opposite is 0. Okay, so like our height is 0 when it's flat. So now we can calculate it very easily. Sine of negative 180 is equal to opposite over hypotenuse, so it's going to be 0 over the hypotenuse, which is 0. Okay, let me just do the next point using the quadrant method, and then I'll just plot the other remaining points. I won't do any working out. So negative 90. We start at 0 and we go clockwise. So our hypotenuse lies here. And this time around, our opposite is the same length as our hypotenuse, and our adjacent is 0. So sine of negative 90 degrees is going to be, our opposite is going to be the same as the hypotenuse, but negative because it's below the horizontal. So opposite is negative h divided by h gives us negative 1. Okay, sine of 0 is 0. Sine of 90 is 1. 180 is 0. 270 negative 1. 360 0. So now let me just plot this. Okay, so as an exercise, maybe try doing what I'm doing here for one of the basic graphs, just to get comfortable with this process. So I'm going to go negative 180, negative 90, 0, 90, 180, 270, 360. And our vertical and horizontals, the maximum and minimum is positive 1 and negative 1 respectively. So sine of negative 180 is 0, negative 90 is negative 1, 0, 1, 180, 270, 0. And now we can just join the dots with a curve like this. And it gives us our standard sine form shape. So now we move on to the standard cos graph, and we're going to once again have intervals of 90 degrees. So cos has the rhyme car from SOHCAHTOA Toa, and cos of theta equals to adjacent over hypotenuse. So I'm just going to list these values. You can try working them out on your own using the quadrant method or a calculator. Okay, so I've just listed some negative values and now onto the positives. Generally, you'll have an interval from 0 to 360 in order to capture the full sine or cos wave. Sorry, this is supposed to be cos theta. I'm getting confused with my own rhyme. So cos theta, cos theta. So negative 180, once again, lies here, and the value of our adjacent is the negative of the hypotenuse. So we would calculate cos negative 180 degrees as negative h over h, which gives us negative 1. 90 degrees, negative 90 degrees is vertical, so here the value of our adjacent is 0, so our trig ratio will be 0. Then it goes 1, 0, negative 1, 0, 1. Okay. So now let's plug and play. Let's put these points. Okay, so just like the sine graph, our cos ratio also has a maximum and minimum of 1 and minus 1 respectively. Okay, so negative 180 is negative 1, 0, 1, 0, negative 1, 0, 1. So our graph would look something like this. Okay, so that gives us our cos wave, and now I'm just going to quickly do the tan graph. So our tan ratio has the rhyme TOA, and that means opposite over adjacent. So before we put any values for theta, I just want to refresh the asymptote story. So we know that the tan graph has a vertical asymptote at 90 degrees. So let's just see what's happening. Now, I first want to check what's happening as theta gets closer to 90 from the left-hand side. So in this picture, we're going maybe 45 degrees, 60, getting closer to 90 from the left. Okay, so value smaller than 90 and we're getting closer from the left. What is happening to our opposite and our adjacent? So as we move in an anti-clockwise fashion, our opposite increases and our adjacent shrinks. So if our adjacent is shrinking, then our overall fraction will get larger and larger. So when adjacent is tending to 0, so at 90 degrees adjacent is 0, when adjacent is tending to 0, this fraction becomes infinitely large. So we can put that down and say as theta tends to 90 degrees from the left-hand side, tan of theta will tend to infinity. So now I just want to see what's happening as theta tends to 90 degrees from the right-hand side. So for angles bigger than 90. So we're going from, say, 100, and then we're going 95, 94, 93. So we're on this side, and our arm is moving clockwise towards 90. The angle is getting smaller. So the same type of thing happens. Our opposite increases and our adjacent shrinks. And then the only thing we must remember is that on this side, adjacent is negative because we're to the left of the vertical. So adjacent is going to be a very small negative number. So all that means is that this tends towards infinity, but it's negative. So negative infinity. So you can write that down as theta tends to 90 degrees from the right-hand side, tan of theta tends to negative infinity. So this explains our vertical asymptote at 90 degrees. The same kind of thing will happen around the 270 degrees. So you can see as we're getting closer to 270, our opposite is increasing and our adjacent is shrinking. So now we can plot some points. So I'm going to let theta go up in increments of 45 degrees. And the reason is because 45 degrees is a nice angle for tan. 45 degrees itself gives us, tan of 45 gives us 1, and other increments of 45 will give -1. So let's plot. So 0, 45, 90, 135, 180. Tan theta, and then we're going to go to 360. So 225, 270, 315, 360. Okay, so if we're trying to check for tan of 0, we can use our quadrant. So our arm lies flat. Our opposite is 0. So opposite is 0 divided by adjacent, which equals the hypotenuse. So 0 over the hypotenuse gives us 0. We said that tan 45 is 1. 90 degrees is a vertical asymptote, and the actual value is undefined if you plug it into the calculator. 135 is minus 1, 180 is 0, 225 is 1, 270 we said was another asymptote, so it's undefined, then minus 1 and 0. So let's plug and play. 0, okay, so I'm just going to put my vertical asymptotes down. I'm going to put in as well 1 and minus 1. So tan of 0 is 0, 45 is 1, and as we get closer to 90, it's an asymptote tending towards infinity. On the other side, 135 is negative 1, 180 is 0, 225 is 1. So from this side, it's negative infinity, and from this side, it's positive infinity. Let's continue. 315 is negative 1, 360 is 0, and we get this. Okay, so if we continue for a few more points, 405 and 450, 495. Then we would get another vertical asymptote here, and the graph would go like this. So you can see that the shape is repeating every 180 degrees. So from 90 to 270 is 180. 315, 360 is 0. Sorry, I made a mistake. It's supposed to then go, so 405 is 1, and then 450 is our vertical asymptote. So I'm going to leave this in the video, I'm not going to edit it out, and it's just to show you human error and also how to check, if you're drawing these things and you see the dimensions are a bit off, just how to spot it. So it would go like this, and our vertical asymptote is actually at 450 degrees. So now it makes sense. 90 to 270 is 180 degrees, and 270 to 450 is 180 degrees, and the shape repeats itself. So now we're going to go on to the parameters and how they affect these graphs.